Swayam Prabha. Digital India. Educated India.
Today we will start a new topic on finite element method. Before we start our topic on finite element, we will focus on a problem just to explain few basic ideas, and this can be considered as a background material. Now consider heat transfer through a fin. Now a fin is attached to a base, you can see, and we are interested in temperature profile in the fin. So this is a realistic fin attached to a base, but let us approximate this fin as a line element. So at one point, that means at the base, let us say the point is I, and this line which is representing the fin, the end point, the point is K, and temperature varies over this line element. And as we know, the fin is a device for extended heat transfer. So basically, it cools the metal or the body of interest, and its temperature profile is basically parabolic or non-linear, and it varies from base to the tip, and basically the fin loses heat to the local ambience, and that is how the temperature varies from a value, say Ti, to Tk through a parabolic variation. Now, if we want to analyze the last picture, we can say that the temperature variation over if this element from I to K can be represented by alpha 1 plus alpha 2x plus alpha 3x squared. This is a quadratic variation. We now so we have basically we need temperature at one more point in addition to I and K, J point, which is located at L by 2. We need help of that point. So we choose the midpoint in addition to the end values to get the following equations. Then when x equal to 0, we have set the first point Ti. So here we can say Ti equal to x is 0, Ti equal to alpha 1. Midpoint is Tj, which is L by 2 away from 0. So Tj equal to alpha 1 plus alpha 2 into L by 2 plus alpha 3 into L by 2 square. And the end point, which is L distance away from x equal to 0, we can say Tk equal to alpha 1 plus alpha 2L plus alpha 3L square. We have to solve these three equations in order to find out alpha 1, alpha 2 and alpha 3. Here directly we can see Ti equal to alpha 1. Then we can substitute this alpha 1 in second equation by Ti, and in the third equation also alpha 1 by Ti. Then we will have two equations in Tj and Tk, two unknowns, alpha 2 and alpha 3, and we can find out alpha 2 and alpha 3. So we finally get alpha 1 is T1, alpha 2 is 1 by L multiplied by minus 3T1 plus 4Tj minus Tk, and alpha 3 is 2 by L square Ti minus twice Tj plus Tk. So alpha 1, alpha 2, alpha 3, these are found out. Now we can substitute alpha 1, alpha 2, alpha 3 in this equation 1, and we can sort of reorganize the values in terms of coefficient of Ti, coefficient of Tj and coefficient of Tk. So then we can write T equal to, if we after substitution alpha 1, alpha 2, alpha 3, if we reorganize the equation and try to find out coefficients of Ti, Tj and Tk, we will find out equation 4, that Ti multiplied by this quantity 1 minus 3x by L plus 2x square by L square plus Tj into 4x by L minus 4x square by L square, Tk into 2x square by L square minus x by L. So this quantity can be called now as N1. This quantity is second quantity. This quantity can be called as Nj, and the coefficient of Tk can be called as Nk. So coefficient of Ti is Ni, coefficient of Tj is Nj, and coefficient of Tk is Nk. This Ni, Nj and Nk are called shape functions or basis functions. Hence, shape functions of a one-dimensional quadratic element are finally obtained as Ni 1 minus 3x by L plus twice x square by L square. If we go back to equation 4, we can see this is Ni. Similarly, Nj will be 4x by L minus 4x square by L square. Nj is 4x by L minus 4x square by L square, and Nk is twice x square by L square minus x by L. The shape functions are employed to represent the nature of the solution within each element. We have taken here as one element. In the schematic, you recall, we took one element. We can take two elements also. Then, the calculation has to be changed slightly. But, if we take one element, we can say Ni, Ti, Nj, Tk, Tj plus Nk, Tk. And we can also find out derivative of this expression for temperature dt dx, which will be given by dni dx into Ti plus dnj dx into Tj plus dnk dx into Tk. So ni dx we can find out, nj dx we can find out, and nk dx we can find out. So it is basically 4x by L square minus 3 by L. This is dni dx into ti. 4 by L minus 8x by L square. This is dnj dx. And 4x by L square minus 1 by L. This is dnk dx. So dtx can be written in this way. This can be also expressed in a compact form. If we say dt dx as q, then we can express this expression in terms of multiplication of a row matrix and column matrix. We'll come to that little later. Now ni, the value which I have got, nj, the value which we have got, and nk, we have plotted that. And dt dx we have plotted. Dt dx we have seen, this is dni dx into ti, dnj dx into tj, dnk dx into tk, that we have plotted. We'll explain these plots little later, but let us look at what I was saying, that dt dx can be expressed as multiplication of a row matrix and column matrix. This column matrix is understood T1, Ti, Tj, Tk, and B matrix is, again, if we look at this term, B matrix is having one row comprising of three elements. First element is 4x by L square minus 3L. Second element is 4 by L minus 8x by L square. And third element is 4x by L square minus 1 by L. So this is B row, and T is a column, Ti, Tj, Tk. So dt dx we can write in a compact way. Now we'll go, if we plot ni, nj and nk over the element. See, ni is given by this. So at x equal to 0, it is 1. But at all other x, you will see it is 0. All other points, all other x's, it is 0. That means nj it is 0, and nk at j point it is 0, and k point it is 0. So that is how ni is 1 at point I, at point j it is 0, point k it is 0. Similarly, variation of nj, if we look, nj at L equal to half it is 1, but at x equal to half it is 1, but x equal to 0 and x equal to L it is 0. So exactly that's what we can see. Nj at j equal to x equal to half, that means at j point it is 1, but it is 0 at I point, it is 0 at k point. Similarly, nk at x equal to L it is 1, but x equal to 0 it is 0, x equal to L by 2 also it is 0. So nk is 0 at point I, 0 at point j, but it is 1 at point k. So this is how within the element shape functions, value of the shape functions vary. And this is the derivative of t dt dx variation over the entire element at j, I, at j and at k. These are the this is how dt dx varies. Major conclusion, as we can say from equation 6, is ni is 1 at I, this is 0 at j and k. Nj is 1 at j and 0 at I and k. nk is 1 at k and 0 at j and k. This is number 1. And number 2, this nijk, summation of nijk at anywhere in the domain is always 1. Okay. So that above 3 shape functions anywhere in the domain between 0 and L, it is always unity. So we can in conclusion say that even though derivatives of the quadratic element are functions of the independent variable x, they will not be continuous. dt dx may not be continuous at interelement nodes. The type of interpolation used here for the temperature is known as Lagrangian interpolation, since this can be generated by Lagrangian interpolation formula. And this guarantees continuity of the function, that is the dependent variable, across the interelement boundaries. So these type of elements are known as C0 element or C0 elements, in which the superscript indicates that only derivatives of 0 order are continuous. That is, only the function is continuous. The elements that also assure the continuity of the derivatives across the interelement boundaries, in addition to continuity of the functions, are known as C1 elements. So C1 elements ensure continuity of the dependent variable and its derivative. C0 element ensures continuity of the dependent variable only. So we have known the properties of C0 elements, and C1 elements also we have mentioned here. Now the functions which are valid for C1 elements are called as Hermite polynomials. Now with this background, let us start our lesson on finite element methods. Let us consider a general representation of a differential equation on a region, say uppercase omega, given by LT equal to Q. We have started renumbering equations again. Background material, we had number from 1 to 9 or 10. This part, again we are renumbering. LT equal to Q. For the one-dimensional heat conduction equation, we can write basically ddx of K is the thermal conductivity, A is the normal area through which heat transfer takes place, into dt dx. So equal to 0. Now we can say if 1 and 2 are identical, then basically symbol L is an operator, which means ddx of Ka into ddx. That is operating on T. The exact solution requires to satisfy equation 1 at all x points. So let us seek for an approximate solution T bar that introduces an error epsilon x. and this epsilon is called the residual. So epsilon x equal to L T bar minus Q. And as we said that this is T bar is a trial solution, is not exact solution as yet. It is approximate solution. The approximate method are centered around concept of setting the residual derivative to weighting function Wi to 0. That means over this domain, if LT bar minus Q, L is the operator, ddx ka ddx, and that is integrated over a domain, say given by V, so integral dV, with the weighting function should be such that it will ask for this quantity to be 0. Wi can be chosen based on the guiding philosophies of different variants of the weighted residual methods. In Galerkin method, Wi are chosen from the basis function used for construction of T bar. So we have already been acquainted with the shape function or basis function, and it is told that for this method Wi will act in such a way that this integral will produce 0. That means it is minimize the residual and elevate T bar to T. That means T bar will evolve as the final solution T. And this weighting function has to be properly chosen so that what we ask for happens finally. And this Galerkin method says that Wi, the weighting function, and the basis function are same. Just to mention here, Galerkin is a very, very well respected name in mathematical science. He was a Russian mathematician who died in 1945, I guess, and he made enormous contribution in mathematical science. We know contributions about Leibniz, contributions of Leibniz, contributions of Newton, and the phenomenal contribution of Gauss. Even today, all the branches of mathematics use Gauss's discoveries. So, in the name of similar stars in mathematical science, we can also mention about Boris Galerkin. As I said, that he was in Soviet Union and contributed enormously, and you can see that today this entire paradigm of weighted residual method of finite elements stand on Galerkin's work. Anyway, let us come back to our discussion again. So consider a steady 2D heat conduction problem in an arbitrary shaped two-dimensional domain which is subjected to various type of boundary conditions. So this is a very arbitrary, shaped body, and this body, we will find out temperature distribution on this body, which generates energy also, considering a uniform heat generation rate. So it has uniform heat generation rate, and the boundaries, as you can see, a part of its boundary, different parts are having different condition. A part of its boundary, for example, this part, temperature is specified, Dirichlet condition, T equal to TB. Maybe another part, the heat flux is specified, SQ part of the boundary. So basically dTdn is specified. Similarly, another part of the boundary, it is basically convective boundary. That means energy is lost to the local ambience, which is at a lower temperature. And this part of the boundary, it is subjected to radiative heat transfer, radiative heat loss. If we can, we'll explain it a little more mathematically here. So governing equation is K del square T plus Q equal to 0. Q is the volumetric heat generation rate, thermal conductivity, del square T plus K del square T plus Q equal to 0. Boundary conditions, as I mentioned earlier, T equal to TB one part, then minus K dt dN, that means heat flux specified on another segment. On another segment, basically it is convective condition, that is the gradient of temperature equal to H into the boundary temperature minus the local ambience temperature. And in another part, basically radiative condition. So this is sigma is Stefan-Boltzmann constant. This is emissivity, epsilon s, T power 4 minus Tf to the power 4. That means the temperature at the edge to the power 4 minus the local ambience temperature to the power 4. That is how the radiative heat transfer is calculated. So we have tried to prescribe all possible forms of boundary conditions on different segments of the enclosure, different segments of the boundary. Now, Galerkin's weighted residual minimization approach, as we have already mentioned, that when we bring in weighting function, which is in Galerkin's approach same as basis function or shape function, K grad square T plus Q dx dy equal to 0, and this Wi is distributed over the domain I equal to n, and this integration is done on the domain of specified domains. So where omega is the solution domain and n is the number of unknown temperatures, in the Galerkin's method the weighting functions are the same as basis function ni, which are used for defining variation of T between the nodal points of an element. So ni is defined if we take an element, the way temperature varies at the nodal points of that element. Element can be in 2D, it can be a triangle, it can be a quadrilateral, in 3D it can be a hexahedral. So at the nodal point the basis functions are defined in such a way that it will give the temperature distribution within the element in a comprehensive manner. So let Txy be the trial solution. Thus the residual equation can be written as area integral over the domain ni k grad square t plus q dx dy equal to 0. So simply the difference between 7 and 8 is that weighting function we have substituted by the shape function or the basis function. Equation 8 is a requirement on ni is that it must be at least twice differentiable so that non-trivial del square t values can be obtained at all locations. I'll go back to the earlier slide again. So ni should be such that it is twice differentiable. That's a mathematical property. However, this requirement can be weakened by integrating this del square or grad square operator by parts. In addition to the convenience of using lower order interpolation functions, so if we do that, we will need lower order interpolation functions. Also, this is called weak formulation because this helps us in implementing the boundary conditions naturally. The form of the equation becomes such that one term of the equation exactly becomes the boundary condition. So we will now integrate ni k del square t dx dy over the domain uppercase omega, and integration by parts has to be carried out together with divergence theorem. So we can write this as ni grad of k del t dx dy, and then integration by parts we can write divergence of ni k del t dx dy minus again area integral of grad ni dot k del t dx dy. And you can see that naturally this is converted into line integral. This divergence ni k grad t will be simply ni k del t del an line integral over the boundary, and del t del n is the temperature gradient in the normal direction on the confining boundary, and this remains as surface integral k grad ni dot grad t dx dy. Now this k grad ni dot grad t can be further written as k del ni del x dot del t del x del ni del y dot del t del y. We get from here dx dy minus we transfer it to the left hand side, then minus ni k del t del n dl. This is basically line integral, and in our original proposition, I'll go back again by 2 slides, we had a q term, that is heat generation term, and that q term now will come here minus surface integral again ni q dt dy. So minus double integral ni q dx dy. So that makes now equation 10, which is the final form of the governing equation. So substitution for the boundary integral terms in terms of given boundary conditions. So in this equation now, we're coming back by again the earlier slide. So this integral plus this is line integral, and line integral means this is falling on confining boundary. Confining boundary means earlier we have defined that it can be convective boundary, it can be specified heat flux boundary, it can be a boundary through which radiative heat transfer is taking place. So in addition to the boundary where temperature is known, that is Dirichlet condition, but that is not a problem. Whenever temperature at the boundary has to be defined, we will directly substitute that by the specified boundary, specified temperature at the boundary. But otherwise we have to define all those del T del N related conditions, which we are calling natural boundary conditions. In this problem, those are either constant specified heat flux condition, that means Q is minus K del T del N. So wherever that is known, or convective heat transfer condition, we have seen Ni into H T minus Tf into dl, or radiative heat transfer condition Ni sigma Stefan-Boltzmann constant epsilon emissivity. This epsilon s is emissivity. This is not the error that we defined while defining our formulation. This is different surface emissivity. T power 4 minus Tf to the power 4 dl. Again, this will be on the segment where it is applicable, plus the heat generation rate equal to 0. And we have identified each term by Roman 1, 2, 3, 4, 5. So where the terms have been numbered as Roman 1 to 5 for our future reference. Now, as we said, that we have defined these boundary conditions, and this is the domain of interest, and in the domain of interest we are discretizing the domain by the triangular elements. So the domain is divided into small elements, each of which has a certain number of nodes, and some nodes will be falling on the boundary, some nodes will be within the domain, and we will use basically a 3-noded triangular element. So this element we have defined, and now you recall the line element that we studied in our background material. There we identified the nodal points as I, J, K. So here also we are trying to identify our nodal points as I, J and K. These are vertices of the triangle. And the 3-noded triangular element for 2D application. 3D application, as I said, obviously elements will be different, will be hexahedrals or prisms, but here it is basically a triangular element, and we can fit in this variation, that T equal to Ax plus By plus C, where constant A, B, C depend on nodal coordinates and the nodal temperature values. The values of A, B, C for a typical element will be given by Ti equal to A xi plus B yi plus C, at J Tj A xj B yj plus C, and tk equal to axk byk plus c. Equations 13, 14 and 15. So now in a comprehensive manner we can write Tijk in a column matrix form. So this will give Tijk, and then from here basically the if we try to take out ABC as again a column matrix, we will be able to get one matrix with xi yi1, xj yj1, xk yk1. This is basically a matrix with 3 rows and 3 columns, 3 by 3 matrix into ABC. So we'll get back equation 13, 14, 15 from the summarized form as 16. Since our major target was to write represent equation 12. So equation 12 is then ax plus by plus c, and if Tijk is given by expression 16, then we can write equation 12 is xy1. Again, I am going back to the earlier slide. Ax plus by plus c can be written as xy1 as a row and ABC as a column matrix, which will give me ax plus by plus c. So T can be written as this. Now in this we can now rewrite for the element E that T is given by xy1 multiplied by, we have to write ABC column matrix. What is the value of ABC column matrix from 16? We can get, it is basically inverse of this matrix into Tijk. So xi yi1, xj yj1, xk yk1, exactly this matrix inverse into Tijk. We have just found out what is ABC. So xy1 multiplied by inverse of this matrix into Ti, Tj, Tk. Now we can call these, which are multipliers of Ti, Tj, Tk, are Ni, Nj, Nk. So necessarily this part, which is coefficient here as the column matrix of Ti, Tj, Tk, will give us the shape functions or the basis functions for the element that are given by Ni, Nj, Nk. So we'll stop here today and we'll find out in the next class Ni, Nj, Nk individually, and we'll see how do they or the shape functions, basis functions, help us finally in solving this problem. So thank you very much. We'll meet in the next class. Thank you.